Hi everyone. At the end of our last lecture, we briefly began Unit 2, where we posed this question that's very different from anything we were doing in Unit 1. Namely, given a general region, which we're going to call R, how do we find the area of that region? And, well, I guess to be fair, we haven't quite gotten to the point of considering a general region, but hey, we're just getting started. What we're specifically looking at for the time being is the following kind of region. Drawing my XY axes here. And so we're interested in a region that's bounded above by some function. And for now, that's really where the most general part of this comes in, because this top function could be absolutely anything. We're really just requiring right now that it lie above the x-axis, because that's what we're going to make the bottom boundary of this region. And then we're also going to pick a couple of vertical lines, which could be anywhere, but I'll sketch them in on either side of the axis, just to give myself a good bit of space here, but they can both be on the same side. And so we'll call these vertical lines x equals a and x equals b, and that gives us this region in here. And I'm not going to shade it in this time because I'm going to draw in here now momentarily, and I don't want to make this too hard to see. But this in here, this shape with this curvy top, that's our region R, and we want to find the exact area that we're going to call A of that region. And right away, this seems like a very difficult problem because, well, like we talked about at the end of the last lecture, we know how to find areas of rectangles, triangles, circles, simple, very simple geometrical shapes, but not a whole lot else. Beyond that, really just combinations of those shapes, which this almost certainly isn't. Not for any general function f of x. The only situation that we'd have an easy time with would be if this happened to be a line. And we can't make that assumption for sure. That could be a quadratic function, it could be a parabola, it could be trigonometric, it could be logarithmic, it could be hyperbolic. All kinds of crazy combinations of those things. Lots of possibilities. So it seems like we've got no way to answer this question. But again, let's think back to Math 1000. And like I was saying when we introduced this topic in the last lecture, we had kind of a similar difficulty there, where we posed this question about finding the slope of a curve at a point, or equivalently, the slope of the tangent line to the curve at the given point. And the way we proceeded there, because again, we were faced with this question that apparently we couldn't resolve, was to say, all right, if we can't answer this question, at least not yet, can we look for a related question, a similar question, that maybe doesn't quite give us the answer we want, but to which we can apply the knowledge we already have with us from an earlier course, from high school math, from wherever. And so, since our only understanding of areas really is in terms of those simple geometrical shapes, what if we took this region R and we approximated it using a bunch of those shapes? Now, we probably don't want to mix a whole bunch of shapes together because that's going to make things a little bit more complicated. And we'd like to do this in a sufficiently systematic way that we'll hopefully be able to apply it to all kinds of different functions f of x and all kinds of intervals from a to b. So we probably want to stick with one shape. Triangles can be awkward to stack, so we probably don't want to do a bunch of different triangles. Circles, circles can be a very useful shape in some geometries, but with this hard corner, these two hard corners that we've imposed here, the way right now at least, we're assuming we've got these vertical lines to the left and right and this horizontal line at the bottom, that suggests that rectangles are probably more appropriate to the way we're setting up the problem. If we were setting it up a different way, maybe circles would be where we'd think about, but probably not the way we're going so far here. All right, so let's draw a bunch of rectangles here to try to approximate this region. So in order to find not the area A, but an approximation of the area A, we will in turn approximate the region R with a number of rectangles. And how many rectangles should we use? Well, that's something we're going to need to explore. Maybe we can get away with just a small number. That'd be great. Maybe we're going to need a whole bunch. So for now, let's just say a number n of rectangles. And if we can do that, and we can do that in a way that seems pretty reasonable, then we do know how to get the area of these rectangles. So we could compute those. So we could compute the area of each rectangle. And then we could get our approximation of the area A. We could estimate A by taking their sum. How good an estimate would that be? Well, again, these are the kinds of things we're going to need to think about. But our first question then is, all right, if we're going to follow this pattern of taking our region, splitting up into a bunch of rectangles, how exactly are we going to pick our rectangles? Because there's lots of ways we could do that. Again, to come back, slide this down a little bit again. I could draw a rectangle here and a rectangle over here and one kind of in the middle here. Lots of ways that I could pack this region R with all kinds of different rectangles. But again, we're trying to come up with a way here that's going to be systematic, that's going to be easily repeated for different functions and for different intervals. So, especially given that we've got this nice horizontal line acting as our lower bound, why don't we use that consistently as one of the sides, or at least portions of it, as one of the sides of each of our rectangles? So in other words, I'm going to draw a rectangle that's going to have a little bit of that x-axis, that interval along the x-axis, as one side. And then my first one might as well use this vertical line x equals a as one of its other sides. And so, in other words, then, I can take this whole interval from A to B. Now I can draw a rectangle here. So let's say from this point to this point. Then I could draw another rectangle here, say from this point to this point. And then another rectangle here, and then another rectangle here, and another rectangle here, and so on, until eventually I'm going to reach this side, where I'm going to presumably want to make this vertical line, x equals b, one of the sides of the rectangle as well. So effectively then what we're doing is we're taking that interval along the x-axis where our region is defined, the interval from A to B, and I'm splitting up that interval in a whole bunch of small intervals, or what we call subintervals. So we're going to divide the interval a comma b, and it's a closed interval, so in other words, this is the same thing as a less than or equal to x, less than or equal to b, if you prefer inequality notation to interval notation. We're going to divide that up into, well, we want n rectangles, so we'll need n subintervals. And we're going to construct our rectangles on each of those subintervals. use those subintervals as one side of each rectangle. When we do that, we say that we've created a partition of the whole interval a comma b. Again, lots of ways we could even do that. We seem to have a ridiculous amount of options here. And so we could make our first interval, or our first subinterval, I should say, really, really big, and then our next subinterval really, really narrow, and then our third subinterval kind of somewhere in between, and keep doing it in a random way. But again, trying to make this systematic, trying to make this easily reproducible for different regions. So unless something screams out to us that we should use all kinds of different widths for each of those subintervals, why don't we pick them all to be the exact same width? So if that's the case, if each subinterval in the partition has the same width, let's call that, say, delta x, because it will be a difference along the x-axis, hence the delta for difference. So if each subinterval has the same width, delta x, then we specifically call this partition a regular partition. All right, so that's going to give us the width of a rectangle, but of course, rectangles are defined by two quantities, the width and, depending on how you want to look at it, the length or the height of the rectangle. So how are we going to pick that other dimension for each of these rectangles? Well, again, seems like we've got options. Let me slide this back down again. Because, for example, if we look at this rectangle here. All right, so there's our width. So we probably don't want to make it just that high, because then we're going to miss out all this stuff above the rectangle. So we probably want to at least make sure that we're drawing it as high as where it touches our curve f of x. So we do something like this. That seems like a reasonable choice. Well, except it's missing this bit here on the top. So if we do that, and if we do that consistently across this whole interval, yes, we should be able to get an approximation of the actual area A, but it's definitely going to be an underestimate. It's going to be lower than the actual area. So you might look at that and say, well, no, that's a dumb idea then. Why do we want to intentionally leave stuff out? So instead we could say, well, why don't we draw so that we touch the highest point, so that we come all the way up to here. And make that red rectangle. Yeah, but that's got its problem too, because now we can see we're actually taking in slightly too much stuff. Okay. Huh. Well, that's probably not what we want either. So how are we going to pick the height of these rectangles? There doesn't seem to be an obvious answer to that question. So, understanding that we haven't resolved that question, let's try investigating. Let's actually get some numbers to work with. It's all well and good doing this in the abstract like we've been doing so far this last quarter of an hour, but, well, it's nice to have a specific example to try to hang these ideas on. So let's do that, and let's try picking the height in a few different ways, and let's see what happens. So specifically then, let's estimate the area bounded above by the curve f of x equal to x squared plus 1, bounded below by the x-axis, bounded to the left by the line x equals 0, so that's the y-axis, and to the right by the line, let's use x equals 1. So we're going to use this as an opportunity to investigate actually two things. There's two big questions we've posed so far. Yes, what we were just talking about, what should the height of the rectangles be? But also, what's a suitable number of rectangles to use in the first place? So let's do this, at least initially, using, let's say, 4 rectangles. Let's do it with a regular partition into 4 subintervals. And let's see what that gets us. Maybe it'll answer some questions. Maybe it'll raise some new questions. Either way, let's pick this up in the next video.